This lecture introduces Laplace transform. We'll talk about the definitions of Laplace transform and how can we derive the Laplace transforms for some of the basic functions. So the main motivations of a transform is actually you want to convert an equation of a given type to another equation that is easier to work with. Then you solve it and then you reverse it back to the original setting, and you interpret the solutions of the equations in the original setting. Okay, but before we can talk about the Laplace transform, we have to talk about the integral transform, because Laplace transform is just a type of integral transform. So integral transform is the transform of the following form right here. And you can see that big F of S is the transform of small f of t. They have different independent variables, keep in mind. And then the function k in terms of s and t is the kernel of the transformation. So the function k multiplied by the function f of t, and you integrate it from alpha to beta, where alpha to beta and beta are given. So this is a definitions of integral transform, right? You transform a functions using integration. Then we can talk about Laplace transform. So Laplace transform is this is the definition of Laplace transform. If you're given a functions f of t, where t is non-negative, then the Laplace transform is denoted using L brackets f of t, or big F of s is the integral from 0 to infinity of e to the negative s of t times t multiplied by function f of t. So again, the Laplace transform exists whenever this improper integral converges. So you need to make sure that this proper integral converges in order to find the Laplace transform for the functions f of t. Okay, and as you remember, this is the function k in terms of s and t, and is a kernel of the Laplace transform. Okay, this is the kernel. All right. So in order to present Laplace transform, you can use either L brackets f of t or L square brackets f of t in terms of s, or you can either use big F of s. Just for people to know that you are using the Laplace transform, not the original functions. And again, the Laplace transform, the independent variable of the Laplace transform is s, versus the independent variable of the original functions could be t or x, depending on the function. Now, using the definition of the Laplace transform, first, we want to find what is the Laplace transform of a functions f of t equals to 1. So you can say big F of s, Laplace transform equals to integral from 0 to infinity e to the negative st times f of t. In this case, it is 1. Okay. And then you know that this is an improper integral, and then you want to transform it into a limit problem. And you call a new variable, let's say a, goes to infinity of the integral from 0 to a of e to the negative st dt. Okay. And then we know that the integral of e to the negative st is going to be equals to 0. So I find the antiderivative of these functions, which is e to the negative st divided by negative s. and you integrate it from 0 to a. Okay, again, we still have the limit problem here. And the limit a goes to infinity. You can replace a into t. Again, you are using t. T is the independent variable in this integral. So you have e to the negative s times a over negative s minus 0, plug into t, e to the negative 1, e to the 0, which is 1, negative 1 over negative s. Okay, and then you will have, e to the negative, still limit of a goes to infinity. At this point, I think you can find the limits at this point when a goes to infinity. E to the negative s of a will be, this will go to 0 because you have a negative here. And you have, so I can try to evaluate this limit now, right? So this, because a goes to infinity and e to the negative infinity, we go to 0. And what left over is just 9 negative of 1 negative a, so this is 1 over s. So big F of s, when f of t equals to 1, is 1 over s. Using Laplace transform definitions. All right, now let's go to the next functions. We want to find the Laplace transform of an exponential function e to the alpha t. And again, we just want to use the definitions f of s, 0 infinity, e to the negative st times e to the alpha t dt, right? This equals to 0 infinity. You combine these two together, so you have t times alpha minus s dt. And again, you find, you convert this into a limit problems when you take a to infinity, and this is going to be from 0 to a, e to the t, alpha minus s dt. Okay. And from here, you are trying to find the antiderivative of this exponential functions, and which is infinity. It's going to give you e to the t alpha minus s divided by alpha minus s. Integrate from 0 to a. And now you need to plug a into a and 0 using the fundamental theorem of calculus to derive, to find this limit. First, I still have the limit a to infinity. Plug a into t, you will have e to the a alpha minus s over alpha minus s. If you plug 0 into t, you will have just e to 0 is just going to be 1 over alpha minus s. Okay. All right. Then now, when you have a is the a goes to positive infinity. And if you want to make sure that this, so e to the a times alpha minus s is the same as e to the negative a s minus alpha. This is where you want to transform these functions a little bit. So a goes to infinity. So this is the same as e to the a negative a s minus alpha, right? And then alpha minus s is the same as negative s minus alpha, and minus 1 over alpha s is the same as negative s minus alpha. Okay. All right. So now we know that a goes to infinity, so this will goes to 0. And then negative and negative will give you a positive value. So the answer for this Laplace transform for this exponential functions is 1 over s minus alpha, where if s is greater than alpha. Because if s is greater than alpha, and this term here will be positive, and these terms here will go to 0 as a goes to infinity. So this is the Laplace transform for the functions e to the alpha. All right, now we're going to try to find the Laplace transform of sine beta t and cosine beta t. Again, we will use the definition, Laplace transform definitions, but we can foresee that the integration will get messy, right? If you have e to the alpha t, st, and sine beta t, and cosine beta t. So a clever way to tackle this problem is we can use Euler's formula. Okay, so what is Euler formulas? Remind us. Euler formulas will tell you that e to the beta ti equals to cosine of beta t plus bt. I should use beta. Plus I times sine of beta t. Okay. So then using Laplace transform, I want to find the Laplace transform of Laplace transform, let's say L e to the beta ti. Okay. So L e to the beta ti, I can use the Euler's formula converted to Laplace of, cosine beta t plus I sine beta t. Okay. Now what? Now, again, I'm just going to use, the definitions of Laplace transform is going to be equals to integral from 0 to infinity of e to the negative st of cosine beta t dt plus I times integral from 0 to infinity e to the negative st sine beta t dt. Okay. Now you can see that the reason why we're transforming this into using Euler's formula is because now we can see is the s of t cosine t and is f of t cosine sine t here. This is the definitions of the Laplace transform of cosine beta t and the sine beta t, except this I. And we're gonna learn how to deal with this complex root. All right, so from here, we know that we can use, remember that we know how to derive the Laplace transform for e to the beta ti. Is that right? And in this case, I want you to treat I as a constant that goes with beta. So the Laplace transform of e to the beta ti, okay, equals to 1 over s minus beta I. Okay. If you have e to the alpha t, the Laplace transform is 1 over s minus alpha. And now I treat beta and I are just constants. So I know that e to the beta ti's is 1 over s minus bi. And the question is, how can we deal with the complex I, right, imaginary part? So we have to find the real and the imaginary part of 1 minus s, 1 over s minus beta I. So in order to deal with this, we use a complex conjugate. So multiply we will have 1 over s minus beta I multiplied by 1 over, multiplied by s plus beta I over s plus beta I. Okay, and this will give you s plus beta I over s squared minus beta I squared, which is I squared is -1 minus -1 is a plus, s squared plus beta squared. Okay, and then you can separate the real and the imaginary part out as s over s squared plus beta squared plus I beta over s squared plus beta squared. And as we know that the real part of this Laplace transform is going to be the Laplace transform of cosine. The real part, right? And this is going to be the Laplace transform. The imaginary part is going to be the Laplace transform of sine. And then down here, we found the real part of the Laplace transform, and we know that is the Laplace transform of cosine of beta t. And this is the imaginary part, and we know that we just take the real parts here, is going to be the Laplace transform of sine of beta t. All right. So we found the Laplace transform of cosine beta t is going to be s over s squared plus beta t of beta squared. And the Laplace transform of sine of beta t is going to be beta over sine squared plus beta squared, s squared plus beta squared. So let's rewrite it down here. So the Laplace of cosine of beta t is going to be s over s squared plus beta squared. Okay, and then the Laplace transform of sine beta t is going to be beta over s squared plus beta squared. So now that we just derived the Laplace transform for 4 basic functions, these are the Laplace transform for sine and cosine. This is the Laplace transform of e to the alpha t, and this is the Laplace transform of a constant function.